By the way, I forgot to hand in the lab from last week. Is it too late to like hand anything in, or should I just forget about it?
So what do you mean it's too late? You're gonna pass it?
I'm a bit confused because like last week, how come there was like no class last week?
Last week was the spring break, right?
Was it? No, that was another time. I think it was 2 weeks ago was a spring break. I don't know.
Oh, that last week, yeah. So we have classes every other week. So the other week is supposed to be like a recitation, but I didn't see anyone send their questions, so I don't have that.
Okay.
So it's like one lab, one recitation. So if you have any questions so next week is a recitation week. If you have any questions, send me your questions before, so we will have recitation. If you don't have questions, then we will don't have class next week. And the lab report due date is 1 week after our lab session. It's not like so whenever the time when we had a recitation is a time when we have the lab report due. All right. Did you guys have the good spring break? Oh, let me see. Oh. All right. Let me share my screen. Let me see what's the chat. Oh, where's the chat? Oh, sorry. Yeah, I can change the lab report for today's lab. So it's supposed to be due next Tuesday. Yeah, I can definitely change that later. So you guys can see my screen, right? So we're gonna have lab 6. Oh, wait. Linear momentum. Linear moment, lab 5. I'm sorry about my background noise. So linear momentum. Wait a second. So today's lab is pretty easy, and hopefully we can finish earlier. So if you click the lab 5, and then there's a simulator, you click on the other window, and we can just play around. So basically you see there's an impulse version 2 lab. So all our labs were from some professors. They collect the simulation labs from different sources. So sometimes maybe you would notice there's they didn't align, but it's okay. Just like a focus on what we do in each lab. Yeah, so you guys already learned the linear momentum or not?
Yes.
Okay, sounds good. So you basically, like we always do, you click begin. You guys are following me. So there is an astronaut, astronaut in the outer space. So if we click, so you can change the mass and the extinguishers force. So what is an extinguishers force? So when the astronaut is moving, so you see the astronaut is holding an extinguisher. So the extinguisher will propel and then according to Newton's third law, the astronaut will gain opposite force, which this force will carry will push the astronaut moving. And then so you can change the so the astronaut's name is Wally. Wally's mass. You can also adjust the extinguishers force, and so we can say like I had a general idea like what it does. So you click activate, then the extinguisher start adding forces to the astronaut, and then it's speeding, and then so after. So you say the extinguisher was firing until the astronaut reached to this line. So after the astronaut reached to this line, the extinguisher stopped giving forces to the astronaut. So from here to here, the astronaut is doing with a constant speed to move. And so you see the photo gate time. So this measures the time between those two lines. So when the astronaut moving from the first line to the second line, how much time does he take? So this is the photo gate time and the momentum gained. So we know the momentum P equal to mv squared. So the momentum is when the astronaut is speeding from the beginning. So in order to simplify all these positions, we say the astronaut start with so this position, the original position of astronaut is 0. So we say here T0, V0, S0. And the first line is the first line, we call it V1, T1, S1. And the second is V2, T2, S2, which is like for convenience to remember when I say them. So this is the position S1, S0 and S1. So this is the distance from S0 to S1. And this is S1 to S2. And the momentum gain for the astronaut is when the astronaut starts speeding from the one position from 0 to 1. So basically you can calculate the P equal to mv squared. The V is changing, but the M is constant. And the momentum you can get also the moment you can just like they can record the momentum for you. So this is basic idea. Let's watch one more time. So speeding, the astronaut speeding. So this record the extinguisher was firing time. Okay, let's see. Any questions? Let me see. Oh, okay. So this is a basic idea. This is what we're gonna do, and we recorded the numbers in our lab report. So that let's go through our lab report. What are we gonna do exactly? So the procedures, go to the above listed URL, click the center, and so basically it tells us to how to use this simulator. I guess you guys are already very familiar. Just click. So like if you want to reset, you click reset here, and then you activate. Then the astronaut start moving. So let's say here. So there are 3 variables. So one is Wallis mass, and another is extinguishers force, the propulsion force from the extinguisher. And the third is the duration of propulsion force from extinguisher. Duration of propulsion force from extinguisher. So what are those 3 variables? The first one is Wallis mass, you can change here. The second is the force Fn is extinguishers force. This is the second variable. And the third variable is the time the extinguisher was firing. So this is the third variable. So 1, 2, 3. You see these 3 variables. And so when we do the experiment, we always hold one variable and keep the other 2 variables constant. So we know all these 3 variables. All variables are easily located on screen with up or down arrows to adjust each variable's magnitude. Let me see. So here the time you cannot adjust, but you can adjust the speed, right? So it says you can adjust the 3 variables by the up arrow and down arrows. But you say that the astronaut's mass it can be very easily adjusted by clicking up and down, and this is the same. But the time for the extinguisher fairing can be adjusted by the adjusting the speed. We know like for a certain let me see. For a certain distance, if you have a bigger speed, then the time will be shorter. The time spent will be shorter. Even it's not like a constant like movement. So let's see. I'll make it bigger. I'll just double check if I'm recording. Okay. So then you begin. Be aware that the photogate time is a time for Wally to travel between the 2 vertical red lines, which symbolize the 2 photogate. So the photogate time is recorded automatically. So it measures the time when Wally passed the first. So this is not a line. This is the photo like a gate. You know, the X-ray, something like they can sense when you pass this. They can sense like what time you enter this area, and the second time when you left. So basically, yeah, but you can also consider it's the line. It's like a racing, and the distance between the photo gate is 10 meters apart. So one more time. So the photo gate time is measured between these 2 lines, between those 2 photo gates. So in this momentum experiment, why should you shut off the why should you shut off the fire extinguisher before Wally reaches the first photo gate red line? Anyone knows why? Why we have to shut off before Wally enter this red line area? So from here, from the first 0 position, original position to the first position, the extinguisher is fairing, which means the extinguisher is propel the astronaut moving, and it's acceleration acceleration process. But why? Do you know why we want to shut off the extinguisher for the first line before the first line? You can answer in the chat. Let's see. Yes, that's correct. So yeah, so I think keep the momentum constant, get the initial speed. Yes, this is like I think they are both correct. So basically, when the astronaut get the speed, and then so every time from here to here, the astronaut always have a it's gaining speed, gaining momentum, and when you shut off before this red line, then the speed, the momentum will remain constant. So from here to here, the it's like it's like the astronaut is doing um, uh, constant how to say the word so basically he has constant speed and he has constant momentum. So from here to here, the momentum didn't gain because the speed is not increasing. So that's why. So in this momentum sphere, so we want we want Wally has a constant momentum, and which of Newton's three laws of motion are in fact here. So like let's recall what are the Newton's three laws. The first is like when the okay, someone's joining now. When the if the object is remain stay. Okay, let's see. Newton's three laws. Okay, so the first law is that every object moves in a straight line unless acted upon by a force. So that means when the object is moving with the speed, then the object will continue moving unless another force stops it um, or make it move faster. Or the object remains still then until another extra force make the object moving. And the second law is the acceleration of an object is directly proportional to the net force exerted and inversely proportional to the object's mass. So the second law is F. We can use the equation to symbolize, which is F equal to ma. The A is acceleration force. F is the force. So, and when we connect the force and the acceleration speed, then we connect the force with its speed, with the time, with everything, because the acceleration speed can be calculated by v over t, right? Do you guys need I write down the equations, or it's just like very so I basically can type here F equal to I type it in the chat. Okay, so the third one, for every action, there's an equal and opposite reaction. So like in the example of Wally, so when Wally is carrying the extinguisher, the extinguisher has a propulsion force. Propulsion force, it gives Wally the opposite direction of the so it has a like a, how does this what I said says for every action there is an equal and opposite reaction. Okay, so what it means, so when the extinguisher is start moving, it gives Wally force to keep him moving forward. So this is the third law. Okay. We just go like we just record like what are the three laws about? What are the Newton's three laws about? So when we shut off the extinguisher, what Newton's law was in effect here? Can someone tell me which the first or second or the third? Okay, let me ask someone. Alexander.
Yes. I would say that it's the first law because it's an object in motion and is staying in motion once we shut off the propulsion.
Oh, correct. That's correct. So the first law was applied in the when the astronauts shut off the extinguisher. Thank you. What's the okay? Next question. What is the fire extinguisher propulsion effort doing to Wally's body mass each second it is spraying? So we just mentioned like which law is applied here? Can someone tell me? Peter. Is Peter here?
Yes, I'm here.
Can you tell us which law was applied here?
Can you repeat that? Sorry, I got a notification.
Okay, you're on vacation?
You want me to read it?
I mean, you can read it. Wait,
Okay,
so this one. You don't, yeah, you tell us the answer.
oh, you want the answer?
Yeah.
Oh, I thought you wanted me to read it. What is fire extinguisher propulsion? Can I see the thing again?
So when the
It's pushing Willie away.
So the where the question is here. So the extinguisher is giving. So when the extinguisher is forced, it's moving, because you know it generates all the air to propel the extinguisher moving, and the astronaut gain a force by the extinguisher. So which Newton's three law was applied here? Do you understand Do you understand this question?
Yeah, is it the one where there's a force, an equal and opposite force is applied?
Yeah. So this
Yeah,
is
that one. I don't know the exact wording, but that's the law.
Yes. So this is the third law. Thank you.
You're welcome.
So next question. So this is the third law was applied here. So how many different method calculation can you use to determine the speed of Wally? So they want you to determine the speed of Wally. So we know. So there are so many ways. Can someone tell me at least one or two? To determine Wally's speed when he arrives here. So you know the first. Okay, sorry. Who is talking?
Just do like distance over time. So it's like 10 meters divided by the photo gate time.
Yeah, that's correct. Thank you. And someone else, like there's another way. Like at least three ways you can, like okay, you can focus on this one, and so you see these two are used. So how about momentum? Can we use a momentum to calculate the speed? So we know the momentum P equal to mv, right? mv squared.
Yeah, someone said it in the chat, but it'll be dividing the momentum by the mass.
And you have to do a square root, remember? Remember P equal to mv squared. Oh, P equal to mv squared. So P over m is the v squared. So you still have to do a square root, right? Thanks, Georgia. So another is
Wait, I don't think velocity is squared in the momentum formula. I think it's just P equals mv, like someone said in the chat.
I'm sorry. Yes, I don't know what. Okay, sorry. Yes, it's P equal to mv. Right, you are correct. Okay, I don't know why I'm thinking mv squared. This is the energy. Yeah. So I think so the third one is okay, thank you for correcting me. So there's another way, like maybe one more way that we can use the extinguisher force, the time here to, and the masses of volley. Can we come up on a third way to calculate the speed of the volley here? So can we calculate the distance here? If we know the distance, it will be much easier, right? So we know so the initial speed is 0, and this speed, we try to calculate this speed. And so let me think. Can we use, so all the, we just try to write all the equations. Let me share blackboard. Wait, let me think first. The time was varying. So it's the t, and we know the force. We can get the acceleration speed, right? We don't need to like integrate a force. So like we can F equal to ma. So you know the m. So let's see, F equal to ma, and you know F and the m, right? So you can calculate a. This is the first you calculate a, and the v equal to v0 plus at. I'm sorry. So plus at. So v0 is 0, and at, a, you know, t, you also know from the time that extinguisher was firing. So you also, from these two equations, you get the speed of the astronaut, right? So let me think let's see, another answer from Shever, integrated force. Integrated force, what do you mean?
Never mind. I was like overthinking the question a little bit.
Okay.
Okay.
Well, thank you. So everyone understand the third way, like we try to calculate the speed of volley. So basically we want to calculate the acceleration speed because we know the force and we know the mass. And then we, after we get the acceleration speed, we know the time, and we can v equal to, yes, that's correct. Then sorry, you're correct. So we try to then we try to calculate the speed by v equal to v0 plus at, and v0 here is 0, so v equal to at. So a is we already calculated from the last formula, and then we time t. Just make sure the time convert, like every time we use time or we use the unit, it should be like unified. Like time here is a millisecond, you have to convert to second, and here is like also millisecond. The photogate time also millisecond. But don't forget to convert to second. So any questions? So here we came up 3 ways for calculating Wally's speed when he reaches to the first red line. So anyone has questions for the how to calculate Wally's speed? Anyone had questions? No? Okay, so how many different methods of calculation can you use to determine the speed of Wally? So here I want to answer all these 3 ways, and you can calculate, yeah, you just list these 3 ways since we already mentioned these 3. And the next question, when is Wally's speed changing during the spraying of the fire extinguisher or when the fire extinguisher is off? It's easy, right? So when the speed is changing? Someone can help me to answer?
It would be when it's on.
Yes. Yes, thank you. So the next one, which of Newton's 3 laws of motion are applied at this moment here? Which one? It's changing. So this is the Newton's 2nd law, because when the so what the difference is, the difference between this one and the question this one, the relationship between fire extinguisher and the Wally. Wait, not this one. This one. Wait. I don't know where it is now. Oh yeah, so here. And this one is like when you have a external space force, so you are changing the speed of the object. So this is the 2nd law. I mean here. So when the Wally speed is changing, this Newton's 2nd law in effect. So here, so using your 3 variables, the mass, the force.
Before we go on, there's like the 3rd question. What is the fire extinguisher propulsion effort doing to Wally's body mass each second it's spraying? Did we answer that one?
Yes, this is yeah. So this is the question. They were asking you why. So while the fire extinguisher is a propulsion, and what effect does the fire extinguisher to Wally, right? So this is Newton's 3rd law, because when the fire extinguisher is moving, and no, I should say when the fire extinguisher is propulsion, like is generated the gases, right? So the gas gives the extinguisher opposite force, and the extinguisher that force keeps the extinguisher moving forward, and then it gives, because the astronaut is holding the extinguisher. So that force also pass to the astronaut to make the astronaut moving forward.
Okay, thank you.
So any questions for these questions? I'm
still not sure I understand about what why it would matter that you shut off the fire extinguisher before Wally reaches the first photo gate, unless what you're wanting is a constant momentum once you get to the photo gate. Because, I mean, like, you can let it run and he can keep gaining momentum through that photo gate. I don't understand why it matters.
So let me try to understand your question. You don't understand why the fire extinguisher has to be shut off when he reaches to the first line.
Yes.
So like, and why is related to the momentum?
I'm assuming that it's related to because if you don't shut it off before then it won't be a constant momentum when he's in the photo gate. But I just wanted to confirm that that's what it's really asking about.
Yes. So when you're so if you keep the extinguishers on, so like they always give you a force, right? Maybe it gives you a same force. I mean, it gives you a same force, but it keeps changing your speed, and your momentum will be changing. So
Right.
yeah.
So the point is that because the momentum's changing, then you're not going to get something accurate. And so you want to shut it off before it gets to the photo gate. So then that way the momentum remains constant.
Yes.
Okay.
Okay. I think that's a good question. So I'm thinking about when we're acceleration from the original point to the first gate, the first photo gate. So the momentum gaining is it's not constantly, it's not constant, right? It's increasing because P equal to mv, V is changing. So can we still use P equal to mv to calculate the speed?
Yes, once it stops growing, once you shut it off.
Yes. So like so this is the momentum gain from the beginning to here. So this is the total momentum the astronaut gained. So you can use this momentum to calculate the speed, I guess. Momentum gain. So anyone has a different opinion here? Yeah, I guess maybe we can, if we have time, we can try to calculate if we get the same speed or not. I'm just like not very certain. But yeah, let's finish the rest of the lab, and then we can do a practice later. So we have 3 variables. By holding to constant and vary only one at a time, create a data set for 5 trials of each variable to 3 data table for the 3 cases. So the first time, so you basically have 3 tables and 3 graphs for this section. And the first one is you keep the force and the mass constant, which means you will change the speed. So if you want to change the time the extinguisher was firing, you keep the speed changing. So you can change different speed, sorry. So this is the one we do for the first variable. So the first, basically, you keep the mass constant, the force constant. T you measure. You just read it from the simulator. You can read it from here. So this T gate, you also record from here. And VW, Wally's speed, can be calculated Mm,
Wouldn't you just do his mass? I mean, the total momentum over his mass.
oh, yeah, you can do that. Yes. Okay. Why don't we just just confirm the momentum one, then we try to see if we are getting the right conclusion before we move on. Because otherwise, I think I'm not very sure for now. Like, let's try to make a simple calculation. We can do it together. So when we activate, sorry, I'm getting my. Okay, so now, so someone try to calculate photo gate. So 10 meter divided by 0.691, I think.
But what you did, the speed was changing through that photo gate. Does that
Yeah,
matter?
I thought you had to turn it off before it went through the gate.
Huh?
Don't you have
Sorry.
to stop it before it goes through the gate? Like, don't you have to stop the fire extinguisher before it goes through the gate? Isn't
Oh.
that the delta T? Is just you just change how long you keep the extinguisher on?
Okay, yeah, I know what you mean. Yeah, I forgot to change that. Okay. Okay, so this is
You messed up again, didn't you?
what
That
happened.
looked delayed.
Okay, one more time. I didn't notice that. Okay, let's see. Okay, this is close.
I don't think you have to wait until it gets to the gate. You can
Yeah,
stop it.
you
It's
just shut it off
really-
whenever.
Wait, what do you mean?
because you can't have it continuing to accelerate once it passes the gate. So you could just stop the extinguisher at any point. You know what I mean? You could stop. You could click reset and then activate and then shut off right away, and it'll tell you how long the extinguisher's been on, and he'll continue to move.
Yes, but you get a different speed. Then you cannot use the momentum to. You see, this is very different. You cannot use the momentum to. Yes, it will have a constant speed. Let's say, but the speed will be different. Oh, let me see. Let me think. Oh, I know what you mean. F equals to. Yes, so we don't have to. But wait a second.
Yeah, but the speed will be different because you're accelerating for a different amount of time every time. Speed will always be different.
Yes, yes. Let me think. I think you're right. So you can stop anytime. You don't have to stop here because, so like anytime when you shut off the extinguisher, the speed will be constant. Like maybe you stop here, the speed is like 10. You stop here, speed is like 15. Stop here, it's like 20. But it will be so. But they all like matches. Like it doesn't mean. So what I mean by that is like you calculate if you stop here in the middle of the screen and the speed maybe is like 10 or something, then it keep constantly moving. And then the momentum gained is just up to here. Momentum mv, yeah. And the extinguisher force F. And the acceleration speed, you can also calculate acceleration speed by using the extinguishers force divided by the mass, and then you use the wait. So V equal to AT. So because this measures the extinguisher's time when it was firing. So you can this one times the acceleration speed, and you can also get the velocity. I guess you're right. I didn't realize last semester I asked everyone to stop at the red gate, the first red gate. Okay, so we use the data we have now, like we try to calculate if we get the same speed. So the first one, 10 divided by 0.7, 14 meter per second, right? and then 964 divided by 70. It's close. Oh yeah. So the momentum divided by mass is 13.7. It's close to 14. And extinguishers force 115 divided by 70. It's the acceleration speed. And times, wow, it's 8.626. Okay, it's 14. Yeah, it's close. I mean, all the three methods to calculate the speed are close. So okay, we can trust that. So the speed you can hear. Let me see if I can move this. Oh, so it gives you a maximum speed, but it doesn't match it to the maximum speed. You still have to calculate. It just, I guess they only give you like a rough speed, because we just calculate. I don't know what result you calculate for the speed.
I think that maximum speed is that if you want the extinguisher to shut off at a certain point, you can get the maximum speed to hit at a thing so that once it hits that speed, the extinguisher will shut off without you shutting it off.
So because we didn't move to the we didn't accelerate to the very end, so we didn't get the maximum speed.
You only got up to 14 meters per second, so you didn't get up to the max speed for it to cut off.
Okay, yes, I see what you mean. So everyone, so yeah, I guess that's right. So what we said here, what we just discussed here is like why we have the maximum speed, but when we calculate, we get a 14 something when the maximum speed is 18. So because remember we stopped in the middle, and so the astronaut still has the potential to reach to the maximum speed of 18, but we didn't, because we didn't let the astronaut to go to the maximum speed. We stopped in the middle. So otherwise it could go to 18 meters per second. So here is the speed of Wally, and we can try to calculate. We have all the three ways to calculate, right? Then okay, the first one is try to, let me see, F equal to, I think here should be divided because, let me type in the chat. So he wants you plot a graph between F times T versus V. So this is what they want you to plot, but we know F equal to MA, and A equal to V over T. So F equal to M V divided by T, right? So we time, so if F times T, F times T.
Well, I think the last column is for impulse. We're supposed to be calculating impulse, which is F net times T.
Huh?
I said, I think the last column is calculating impulse. So it would be F net times T, delta T.
Impulse.
Yeah, it would be impulse. It's the formula for impulse. Like even on the lab, like on your tab right there, it says impulse lab. So I have a feeling it might be impulse. Like on the tab, I'm saying, like on your browser that I can see right there for the actual lab itself, it says impulse lab.
Impulse.
Mm-hmm. And that's the formula for impulse, is that last column. So I think that's what we're calculating.
Oh, I didn't know impulse has a formula.
Yeah, it would be it's F net times delta T.
Oh, okay. Let me double check. So I was trying to derive from the equation impulse formula. I guess you're right. Okay. Oh, the change in momentum. Okay, I learned. So yeah, so if you know the impulse formula, then you can have F times T. This is the impulse. And then otherwise you can just like me use like a very like a slow method to derive F over T, F times T. So you'll have, can you see the chat? So I type a few things. So F equal to MA, A equal to V over T, and F equal to M times A, which is V over T. And then you take times T on both sides. You have F times T equal to MV. But I think the impulse formula is much useful and very straightforward. So you record the data here. And let me see, the second, so you keep one constant, okay, keep one variable to constant. So in the first table, you have the force and the mass, they are constant. So you have 3 tables, so 3 graphs. And the second one will be the mass and the time hold constant. So you change the force, Extinguishers Force. So you also have a same table.
How would you get the time to be constant for the fire extinguisher?
You just keep the, I guess you keep the speed constant. So how do you keep the speed constant? So last time what I did was try to like stop at the same time, always stop at the red light, stop at the photo gate. So it kind of helped me to measure what time to stop.
Could you just lower the maximum speed to a point where the maximum speed wouldn't be affected, and then you would be able to change the force? And yeah, you don't need to set it that low, but you could set it to like 7 or something, and then change the force, and then it would cut off.
Remember we said the maximum force is like a maximum. You like remember when we are using 18, we calculated speed is 14 because we stop in the middle. Remember, because if we stop like last time we stopped here, we calculated 14, but maybe it reaches to, I don't know, maybe somewhere here after it disappeared. Then this is 18.
Yeah, no, that makes sense. Sorry, I didn't think about that.
Yeah. So I guess like the best way is to like you have a like a reference. It either stop here or stops here. So you can have like a reference every time you stop here. You make sure every time you shut off the extinguisher at around this position, and you can have a rough similar like a constant, what we considered as constant speed.
The thing is that when you do reduce the maximum speed to, let's say, like 5 meters per second, it will automatically like stop the fire extinguisher like midway. Like it won't go like past the red line.
Oh.
So would that be like the thing? Because if you change it to 5 meters per second, you'll see that the fire extinguisher will just stop midway automatically.
Let me see. That would be make our life much easier. Also,
Yeah, it just stops. Yeah.
But the time would change because the extinguisher's force would not get to 5 meters in the same amount of time. So it wouldn't give.
Yeah, when you change the force. Yeah.
So for the purposes of keeping time consistent, we would have to just do it at the same spot.
3044. Let's see. Change the Extinguishers Force. 3044. Okay. Okay, so we can use that, so we don't have to estimate everything. So thanks for the input. So we can keep the maximum, like keep it the maximum speed lower value, and the extinguisher will stop automatically in the middle. So that gives a constant speed like 5, and then we can measure the force and the like we can measure the force and measure different force. What do we want to do? Measure the force. Yes, I guess the second one is force. So the first table is the last column is F times delta T. So in the second table you have this F NET. So it's F only. And the third one is, I don't think, wait. So you guys have 3 tables. And the first one is like this table. The second one is same. And this one is F. Wait, you don't have to take this one, this column, because you already have F here. Okay, I guess the first table is like this one, and the second table is like this 2V, and the third table is this 2V. But you will change the MV or F in a third and a second table, but you don't have to include this column.
I think you should be including the last column for all of them, because you're still going to come up with an impulse for each one of the trials. What you're looking at below is for the graphs, and for the graphs you're not going to care about the impulse, but I mean, does that mean we still shouldn't calculate the impulse for the other two?
Let me see. I thought each table you get one graph, or each table you have 3 graphs. I think each table has 1 graph. So the first one is like you have the impulse, and you create the impulse versus speed, right? So can you repeat that?
What I'm saying is that the table should have all of that information for every trial, for everything, for all 3 tables. It's just the graph won't use the impulse that you calculate for the other 2 tables.
Yeah, you can also do that. Like you keep the same table, but you change different variables in each table.
Right.
Yeah, because this lab is like a linear momentum. But I don't think it's necessary. Do you think it's necessary to keep this column?
I don't know. I'm the one being told that what to do here. If you don't want us to, it'll save me time. But it just seemed like it wasn't suggesting that you should lay it off just because it wasn't going to be in the graphs later on. But whatever.
Okay, yeah, you can keep all of them.
But isn't the first graph, isn't graph 1 right there? Impulse versus speed. So it is in the graphs, right?
Yeah.
It's only in the first graph. The other 2 it's not in. So we don't necessarily need to calculate the impulse, I guess, but I mean, whatever.
Wait, should we be doing all 3 of these graphs for all 3 experiments? Or
so each time we will have 3 tables, right?
Yes, 3 tables, yeah.
So the first table is like we do this table, the given, and this graph. And the second one, we get a table, because every time we have different variables. So that's why we have to keep 3 different tables. We cannot.
So you're saying graph number 1 should be for table number 1, graph number 2 should be for table number 2. So we're not graphing all 3 of those for each graph. Okay, that makes sense.
Yeah. Because otherwise, if the first time, what is the variable? So the F is constant. The speed is variable. So F is constant. If we do the second and third, then the F will be always constant. I don't know what graph will have the speed. But anyways, so like we have 3 tables. Each table give you 1 graph. So they're like corresponding, like the first one, you see, this is 1. Well, you keep the F and M as constant, and you create a graph. like the impulse versus speed, right? The second one is m and t hold constant, and you plot a graph f versus a speed. And the third, when you keep f and t constant, wait. Okay, f and t constant, and you plot m over speed. So that's it for today's lab. Any other questions? Oh, sorry, I didn't see the chat. Oh, yeah. Oh no, it's due next Tuesday. Sorry, I will change later. I'll change the due date next later after the class. Let me take attendance. Any other questions? Calculate the graphs to the momentum. Compare those graphs to momentum. Let me see. Momentum P equal to mv, right? Oh, you mean here, compare the graph to the momentum volley. How to compare the momentum with this V. Oh, so I guess here, so okay, so the first one is F T equal to mv, right? Mv is momentum, right? I have to write it down, I guess. You guys can see the chat. Oh, where is my share screen? So the first one, let's say the first one is F times T, the impulse, equal to mv. So when you wait, not equal to mv, equal to mv. Well, mv equal to Paul, the momentum. So basically, so the y-axis represents the momentum. I guess I just try to relate in the equations, unless you guys have other inputs. So the second one, so for the first one, because this one F times T, the impulse equal to mv, right? And then you have mv equal to the momentum. So the y-axis, the y represents y-axis represents the momentum, and the second one is F versus the speed. F versus speed. So the second, how we try to relate. You mean the second? Oh, say, Anika, you ask the second or the first one? You can either calculate if you're, so in general, if you ask me how do we find Wallis speed? So either you can calculate, as we mentioned, use the this one divide the distance divided by time, or momentum equal to mv, or use this one, or if you keep it slow, you can just read it from here. So I'm not sure, can you specify your question? Because I'm not sure which one are you asking? Like yes, the maximum speed is Wally's speed, but you have to make sure Wally's speed really give all the maximum speed, because you cannot stop in the middle. You have to wait until so you can, if you keep the speed low, then you can say yes, the max speed is Wally's speed. But if you didn't keep it low, let's say it keep the maximum is 20 or 18, if you stop somewhere, then that max speed is not Wally's speed. I don't know which part you are talking about, because different like motion, different position, they have different. So what I can tell you is, if you keep the, like, let's say if you keep the maximum speed is 5 meters per second, then when Wally stops here, not stops, like reaches to here or here, it has a constant speed. Yes, you are correct. But if you keep the maximum speed as 18 or 20, so then from here to maybe here, I don't know, like you have to really observe like when the extinguisher is still working or not. And you can tell if Wally's speed is constant or not. That's all I can tell you. Do I understand your question correctly? I need to charge my.
So I wanted to know that.
Sorry, I cannot hear you.
Is
Can you like it's a little small. I already reached to the maximum volume, but can anyone else? I mean, can you say that again? Sorry. Maybe my noise is too much. Anika, are you speaking? Oh, sorry. Let's see. Yes. But it depends on which part you're going through. So you know why your speed is constant. You have to understand that you don't like really take my word as like something, because this is it relate to the motions. It's not only like I give you a number that is constant. You have to understand the process of the momentum. Okay, I guess. But if you like have any questions from this lab, you can always like write me email, or you can ask me questions. And also, if you have a question for next week, you can send me questions before, so we can work together. I think you guys are much smarter than I am. We can try to organize this recitation. Also, I learned a lot from you guys. Nafila's question. Nafila. Okay. So I guess I try to work on that. So F versus Wally speed. F equal to speed of Wally. So the second, what is a variable? Second, F is variable. Oh, I remember last time what I did. F equal to, so F equal to mv over t, right? And then F equal to P over T, because P equal to mv. So that's how I compare this. So if you're, let me see. What forces cause change in momentum. If speed is constant, momentum does not change. B. Force causes change in momentum. Yes. So because the mass is constant, I guess mass is constant. Then the F will change the speed of Wally, so the momentum will be increasing. If Wally is speeding, the momentum will be increasing because the so there are two factors can affect the momentum. One is the mass, another is speed. When we keep Wally's mass is constant, the speed is changing because of the forces. Then the momentum is changing, it's increasing. So the third one is easy because we can say F. So it's P equal to mv. So m over v is Okay, P equal to mv. So m versus v should be a hyperbola. Right? Let me see. So the third one, the variable, what is the variable? F and T constant. And no. So the third one, T. A third one should be, so the momentum is the is m times v, which is the, in the graph it shows the area and the x and y axis. Okay, let me share whiteboard. So try to see. This is V. I don't know what maybe a graph like this. Let me see what graph it should be look like. It's F and T constant, so the speed is changing. Wait, F equal to mv over T, and F and T constant. F and T constant. So F and T constant, that means FV is constant. So that means, so it's from this equation, if F and T keeps constant, so MV will be constant, right? If so, FT equal to MV, because these two are constant, and then this will be constant, equal to P, the momentum, maybe I spelled wrong, is constant. It's constant. So you will have a hyperbola. So let me draw something. I guess you will have like a graph like this. So what I mean, like this is S, X, wait, X, Y. So this is so what compared to the momentum should be the area like this, in this area. But anyways, so this graph represents the, how to say, it should be, so this graph, like this graph is M versus V. But these two times together is the momentum, right? And we also know the momentum is constant by giving Ft is our constant. I guess you can see the momentum for the third graph is the area under, so the area under this line are the momentum, because we know this is the momentum when the speed equal to x and the mass equal to y. So what do you guys think? I really have to charge. Someone. Okay, I'll take a screenshot because I think it saves more time for taking attendance. Then I think that's all right. 1, 2, 3, 4, 5, 5. 1, 2, 3, 4. Wait a second. Stop sharing. Okay, 1, 2, 3, 4. 20, 24 seconds. Okay. Okay, I think then I can match your name, so I don't have to like everybody wait here. So if you have any questions, for next week, just send me email and we can meet next week. If there is no questions, then there is no meeting.
Did you take attendance yet?
Yes, I took a screenshot, so you guys don't have to like be here to like say you are here.
Okay, did you just take the screenshot or like 10 minutes ago?
Just now.
Okay.
Okay, thank you.
Thank you. Have a great week. Bye.
Thank you.
Take care. Thank you.
Thanks everyone.